Hello students, in this session we will discuss direct and bending stresses in a column section. In previous sessions we discussed what is direct and bending stresses. So basically whenever a column section is subjected to eccentric load, direct and bending both type of the stresses will be developed in a column section. In previous sessions, we also solved numerical to calculate maximum and minimum stresses developed in a column section which is eccentrically loaded. But in previous sessions, we discussed eccentricity of the load in one direction only. Now, in this session, we will discuss eccentricity of the load about both the axes. So, let's formulate equation to calculate stresses at all four corners of the column section. Here, a rectangular column section is given. A, B, C and D are four corners of the column section and we need to formulate equation to calculate stresses at all these four corners of the column. The column section is subjected to load P, which is eccentric about both the axes. You can see that load P is away from y-axis as well as x-axis. It means we can say that eccentricity is in both the direction. So we know that whenever a column section is subjected to eccentric load, direct stresses as well as bending stresses both will be generated. And total stress developed in a column section due to eccentric load is summation of direct stresses sigma 0 plus bending stresses sigma b. Okay. Now, in previous sessions, we discussed eccentricity of the load about one axis only. It means the stresses developed in one direction only. Okay. Now here in this case, eccentricity of the load is about both the axes. That's why here in this condition, bending stresses will be developed in both the axes. Okay. So we can say that because of this eccentric load, total stresses developed in this column section will be summation of direct stress and bending stress. Here direct stress will be sigma 0 and bending stress will be summation of bending stresses developed in x-axis direction and bending stresses developed in y-y direction. Okay. Now we will consider all compressive bending stresses as positive and tensile bending stresses as negative. So let's start with corner D. Okay. So first of all, here is the equation to calculate stresses means total stresses developed at corner D due to this eccentric load. Okay, so total stresses developed at corner D due to this eccentric load is summation of direct stress and bending stress. So we know that sigma 0 is direct stress and sigma bx and sigma by are bending stresses which are developed due to eccentricity of this load about both the axes. Okay. Now, for this sign convention, we need to push this load point and we need to target this first quadrant. Okay. So, by pushing this load point, okay, here in first quadrant, both the axes means x-axis and y-axis, both the axes will be compressed and because of compressive force along both the axes, compressive bending stresses will be developed. Okay, that's why here I am considering sigma bx and sigma by both as positive. So, final equation to calculate stress at corner D is equal to sigma 0, which is direct stress, plus sigma bx because bending stress is developed in x-axis directions is compressive, plus sigma by, again bending stress developed in y direction is also compressive. Okay, now let's move to corner B, and for formulating equation for calculating stress at corner B, we need to target this third quadrant and here is the equation. So sigma B is equal to sigma 0, which is direct stress, minus sigma Bx minus sigma By. Here I am taking both the bending stresses as negative. For that, we need to again push this point. Okay, and by pushing this point, you can observe that both the axes of this third quadrant will get stretched. It means tension will be there. And because of that, bending stresses developed in this third quadrant due to this eccentric load will be tensile in nature. And we are considering all tensile bending stress as negative. So I am considering sigma Bx and sigma By in this third quadrant as negative. So here is final equation of stress at sigma B is equal to sigma 0 minus sigma Bx minus sigma By. Now let's move to corner A. And for corner A, we need to consider second quadrant. Okay, so stresses at corner A is equal to sigma 0 plus sigma Bx minus sigma By. So again, we need to push this load point. Okay, and by pushing this load point, you can observe that x-axis of the second quadrant will be compressed. So in x direction of the second quadrant, compressive stresses will be generated. That's why I am taking sigma Bx for a corner A as positive. And by pushing this in second quadrant, vertical axis means y-axis will get stretched. So because of this eccentric load in second quadrant, tensile stresses, bending stresses will be developed. So I am taking tensile bending stresses in second quadrant due to this eccentric load as negative. Okay, so here is the final equation to calculate bending stresses at corner A, which is sigma 0 plus sigma Bx, okay, because in x direction compressive bending stresses will be developed, minus sigma By because along y direction tensile bending stresses will be developed. Now let's move to last corner, that is corner C. And here is the equation for calculating bending total stresses at corner C. Sigma C is equal to sigma 0 minus sigma Bx plus sigma By. So again for that we need to push this load point. By pushing this load point, you can observe that x-axis of this fourth quadrant due to this eccentric load will get stretched. It means along this x-axis of this fourth quadrant, tensile bending stresses will be generated. Okay, so I am taking tensile bending stresses in x-axis direction as negative, and by pushing this point means because of this eccentric load, vertical axis of this fourth quadrant will get compressed, and due to that here in fourth quadrant, due to this eccentric load, compressive bending stresses will be developed in y direction. So I am taking sigma By as positive over here. So these are the equations that we will use to solve our numerical to calculate stresses at all four corners of the column section, which is eccentrically loaded about both the axes. Okay, so let's calculate one numerical. Here, a masonry pier of size 3 meter by 4 meter is subjected to compressive load of 600 kilonewton as shown in the figure. So figure is already given, and the column section is subjected to compressive load P, which is 600 kilonewton. Okay, the load is in first quadrant. Okay, now width of this column section is 4 meter and depth or thickness of this column section is 3 meter. Okay, now you can see that this point load is 1.2 meter away from this y axis. It means eccentricity of this load about x-axis is 1.2 meter. It means Ex is 1.2 meter. Now the load is 1 meter away from the x-axis. So eccentricity of this load about y-axis is 1 meter, which is Ey. Okay. Now we need to calculate stress produced at each corner of the pier. Okay. These are the equations that we will use for calculating this numerical. First of all, we need to use all these equations to calculate stresses at all four corners of the column section as we discussed in previous slide. Okay. Now, we also need to recall equations that we discussed in previous sessions. So, sigma 0 is a direct bending stresses. Sigma 0 is P by A, where P is the axial load. Now, sigma Bx is bending stresses developed in xx direction due to vertical eccentricity Ey. And equation to calculate sigma Bx is m upon zxx, okay, which is equal to, here m is moment and moment is equal to P into Ey and zxx is equal to Ixx upon d by 2. Now here is the equation to calculate sigma By. Sigma By is the bending stresses developed in y direction, which is equal to m upon zyy. Okay, m is the moment, which is equal to P into Ex, means eccentricity in x direction, and Zyy is equal to Iyy upon b by 2. Okay, so these are the equations that we will use to calculate stresses at all those four corners of the column section. So let's start with calculating sigma 0. Here is the equation to calculate sigma 0, which is direct stress. It is equal to P by A. Value of P is already given. It is 600 kilonewton and area of this column section is B into D, which is 4 by 3. So I am getting sigma 0 is equal to 50 kilonewton per meter square. Now, for calculating sigma Bx and sigma By, first of all we need to calculate Ixx and Iyy. So for calculating Ixx, which is moment of inertia of this column section about xx axis, it is equal to Bd cube by 12. Here in our case, B is equal to 4 meter and D is equal to 3 meter. So Ixx is equal to 4 into 3 cube by 12. So I am getting Ixx is equal to 9 meter raised to 4. Similarly, let's calculate Iyy. Iyy is the moment of inertia about y-axis, which is equal to dB cube by 12. Here in our case, D is 3 meter and B is 4 meter. So I am getting Iyy is equal to 16 m raised to 4. Okay. So let's put all this value in equation of sigma Bx to calculate bending stresses in xx direction. So here is the equation. Sigma Bx is equal to m upon z, which is equal to P into Ey upon Ixx into d by 2. Value of P, which is already given, 600. Eccentricity in y direction is 1 meter. Ixx that we calculated, it is 16, and d by 2 means depth by 2, which is 3 by 2, 1.5. So I am getting sigma Bx is equal to 100 kilonewton per meter square. Now let's calculate sigma By. Sigma By is the bending stresses developed in y direction, which is equal to m upon z, which is P into Ex upon Iyy into b by 2. Okay, equation we already discussed in previous sessions. So let's put value of P in this equation. So value of P, which is given, 600. Eccentricity in x direction is 1.2. Iyy, as we calculated, it is 16, and b by 2, here in our case B is what? 4 meter. So 4 by 2 is 2 meter. So I am getting bending stresses in YY direction, which is sigma By is equal to 90 kilonewton per meter square. Now, using all these values, let's calculate stresses at each corner of this column section. So here, these are the values that we calculated. Okay. So let's start with corner D. Okay. At corner D, we will get maximum value of the stresses. Okay. So because the load is nearer to corner D. Okay. So to calculate total stresses at corner D, here is the equation. Sigma D is equal to sigma 0 plus sigma Bx plus sigma By. Okay. Recall that we discussed in previous session while formulating equation. Here, by pushing this point, both the axes of the first quadrant will get compressed. So here, due to this eccentric load in first quadrant, compressive bending stresses will be developed in both the directions. That's why I am taking bending stresses developed in x and y both direction as a positive. Okay, so value of sigma 0 we calculated, it is 50 kilonewton per meter square. Sigma Bx is 100 kilonewton per meter square and sigma By is 90. So total stresses developed at corner D is equal to 240 kilonewton per meter square. Here I am getting value of total stress positive. It means we can say that at corner D, stresses developed will be compressive in nature. Now let's calculate total stresses at corner B. Okay, at corner B, the stresses generated will be minimum. Okay, and here is the equation. Sigma is equal to sigma 0 minus sigma Bx minus sigma By. Again, for calculating stresses in this third quadrant, we need to push this point. So if we push this point, then both the axes of this third quadrant will get stretched. It means in both the axes, tensile bending stresses will be developed. So I am taking negative value of tensile bending stresses. So let's put value of sigma 0, sigma Bx and sigma By as we calculated in this equation. So I am getting total stress developed at corner B is equal to minus 140 kilonewton per meter square. Here this negative value indicate that the generated stresses are tensile in nature. Okay. So let's move to next corner at point A. Here is the equation to calculate stresses at point A or corner A. Sigma is equal to sigma 0 plus sigma Bx minus sigma By. So, for corner A, we need to consider second quadrant, and by pushing this point, okay, x-axis of the second quadrant will get compressed. So compressive bending stresses will be generated in second quadrant due to this eccentric load. So I am taking sigma Bx as positive. In opposite manner, by pushing this point, y-axis of the second quadrant will get stretched and tensile stresses will be generated. So I am taking sigma By as negative. Okay. So I am getting value of sigma at corner A is equal to 60 kilonewton per meter square. Here I am getting positive value. It means stresses developed at corner A is compressive in nature. Now let's calculate bending total stresses at corner C. Here is the equation. Sigma is equal to sigma 0 minus sigma Bx plus sigma By. Okay. Again, for sigma Bx and sigma By, we need to push this point. Okay, by pushing this point, fourth quadrant, okay, x-axis will get stretched. Means in x direction of fourth quadrant, due to this eccentric load, tensile stresses will be generated. So I am taking sigma Bx in fourth quadrant nearer to corner C as negative. and the y-axis get compressed. That's why here I am considering sigma by, which is bending stresses developed in y direction as positive. So by putting the value of sigma 0, sigma bx, sigma by, I am getting total stress at corner C is equal to 40 kilonewton per meter square. So we have calculated bending stresses and direct stresses developed at all four corners of the column section. Now let's draw stress distribution diagram. So here this rectangle is a rectangular cross section which is given. A, B, C and D are the corners of the column. Now let's start with face AD. Okay. So here at corner A, stresses generated are 60, which are positive. Okay, so here I mentioned 60 kilonewton per meter square, which are the total stresses developed at point A. Now at point D, stresses developed is 240 kilonewton per meter square, which is again positive. So here at point D, I also mentioned 240 kilonewton per meter square. Okay, and this is the stress distribution diagram on face AD. Okay, due to the stresses developed at corner A and corner D. Now let's move to face D and C. Okay, face C. So at D again, stresses developed 240 kilonewton per meter square, which is positive. At C, stresses developed plus 40 kilonewton per meter square. So here is the stress distribution diagram for face C. Now at face AB, so stresses developed at corner A is 60 kilonewton. Okay, so here I mentioned 60 kilonewton, and total stresses developed at point B is minus 140. So here I mentioned minus 140 kilonewton per meter square. So here is the stress distribution diagram for face AB. Now let's draw a stress distribution diagram for face BC. So at B again, total bending stresses minus 140, and face C, bending stresses are plus 40. Okay, so this is the stress distribution diagram of face BC. Okay, so this is end of this session. Thank you.